We saw earlier how to get the stationary point of a function. In action physics, we will need to generalize that in the case of an integral of a function. Of course, I see that g depends on f. That is, if I take, for instance, f equal x or f equal x squared, I will have a different value for g. This means that g is a function of the function f, or more precisely what we call a functional of f. In the same way that we looked at the variation of f with respect to x, we can look at the variation of g with respect to f. For this, we express g for a function f plus an arbitrary function n of x. What matters is the difference between these two quantities. So far I have said nothing about n. It could be any function you want. But in the same way that before we were considering small variation of x by adding a small epsilon to x, we will consider small variation of the function f. So for that we will multiply the function n by a small number epsilon. As we did before, we can expand this difference as function of epsilon. Because it's a difference, there is no zeroth order, and the first order will be in epsilon, and then there will be other higher order in epsilon squared, epsilon 3, etc. We have kept only the first order and put everything else in the higher order. K doesn't depend on epsilon, but it will depend on the choice of the function f. By analogy with the case of a function, we have g stationary when the first order is equal to 0. In many cases, as in action physics, we have to search for the function f which will leave the functional g stationary. And that we write in a formal notation as this is equivalent as to look for the stationary point in the case of a function.